We'll start in about a minute. Okay, it's 8 o'clock already. Today we'll be in section 6.3a, the first part of factoring special products. So a reminder, factoring is the reverse process of multiplying, and you can check your factoring by multiplying. And the first step in factoring is to factor out the greatest common factor of all of the terms. And some special products are perfect square trinomials. And perfect square trinomials have two forms. One form is a to the second plus 2 times a times b plus b to the second. And the other form is a to the second minus 2ab plus b to the second. When you factor the two perfect square trinomials, you'll get identical factors. So when we factor a squared plus 2ab plus b to the second, the two factors are a plus b times a plus b. But you can, if you want, you can write that as the quantity a plus b to the second. So either way is acceptable. The other perfect square trinomial, a to the second minus 2ab plus b to the second, its two factors are a minus b times a minus b, or a minus b squared. And you can verify that these formulas work. If you square a plus b and simplify, you'll get this perfect square trinomial. Okay, if a trinomial is not recognized as a perfect square trinomial, then it can still be factored by using the AC method that we started talking about yesterday. So let's try that out. Let's factor some trinomials. So this one, 9x to the second plus 12x plus 4. Notice that the first term, 9x to the second, is a perfect square. We refer to this as a perfect square because if you square the term 3x, which means 3x times 3x, we get 9x to the second. Notice the term on the right, 4. 4 is a perfect square because 2 to the second equals 4. So in general, if you square an integer or raise an integer to the second power, the result is called a perfect square. And the same is true for variable expressions. If you square a variable term, then the product is called a perfect square. So if this is a perfect square trinomial, then the middle part, the plus 12x, will have this form up here. This is the form that we're testing, a to the second plus 2 times a times b plus b to the second. The term on the left, a to the second, is a perfect square. The term on the right, b to the second, is a perfect square. In order for it to be a perfect square trinomial, the middle term has to be plus 2 times a times b. So in this case, the term that takes the place of a in the formula is 3x, and the term that takes the place of b in the formula is 2. So we want to see if the middle term is the same as 2 times a times b. This has the form 2 times a times b. And so now the question is 2 times 3x times 2 equal to 12x? Yes, it is. 2 times 3x is 6x. 6x times 2 is 12x. So this is a perfect square trinomial. So that means the two factors have the form a plus b times a plus b. In this case, 3x plus 2 times 3x plus 2. Okay, so I mentioned that you can still factor a perfect square trinomial by using the AC method if you don't notice that it could be a perfect square trinomial. So we'll go through that since we need to practice the AC method anyway. Let's apply the AC method. The AC method is a very good method for factoring trinomials. And if you follow it to the T, you will never fail using the AC method. That means if you don't make any mistakes in the process. Okay, so in this one, if we apply the AC method, we multiply 9 times 4. 9 times 4 is 36. Then find two numbers whose product is also 36, but whose sum is 12. So you can go through the systematic process, like 1 times 36, but 1 plus 36 is 37. 2 times 18 is 36, but 2 plus 18 is 20. 3 times 12 is 36, but 3 plus 12 is 15. 4 times 9 is 36, but 9 plus 4 is 13. Then 6 times 6. 6 times 6 is 36, and 6 plus 6 is 12. So those are the pair. 6 times 6 is 36, and 6 plus 6 is 12. Okay, I'll mention something that's true about using the AC method when factoring a perfect square trinomial. And it seems to make sense. The two integers are going to be the same. In this case, 6 and 6. Why does that make sense? Well, if the two binomial factors are the same, it seems reasonable that the two integers, it's not far-fetched that the two integers that you need are also going to be the same. Okay, so using the integers 6 and 6, we transform the trinomial into a quadrinomial. Replace the plus 12x with plus 6x plus 6x. And then factor the quadrinomial by grouping. Out of the first two terms, 9x squared plus 6x, the greatest common factor is 3x. So we factor 3x out. And then the binomial, the first term in the binomial can be found if you divide 9x to the second by 3x, and that's 3x. Then the second term, divide plus 6x by 3x, that's plus 2. Bring down the middle operator of addition, and then In the third and fourth terms, factor that by grouping. Out of 6x plus 4, the greatest common factor is 2. And the binomial 6x divided by 2 is 3x. 4 divided by 2 is positive 2. And then the last step, since the binomial factors match, we factor out 3x plus 2. The other binomial is 3x plus 2. Okay, so be reassured that even if you don't recognize a perfect square trinomial, you can still factor it by using the AC method. Sometimes, though, if the numbers are large, then it could be time-consuming if you don't recognize it as a perfect square trinomial. Okay, here's a trinomial. Keep in mind, though, if it's a perfect square trinomial, the term on the left is a perfect square, like this one. 25y to the second is considered a perfect square because we can square the term 5y to get 25y to the second plus 16. 16 is a perfect square because when we square 4, we get 16. But keep in mind, if you have a trinomial, and if the term on the left is a perfect square and the term on the right is a perfect square, it doesn't automatically mean that it's going to be a perfect square trinomial. The middle term has to have the right form. It has to follow the pattern of the formula. Okay, so if this is a perfect square trinomial, then it's of this form up here. It's of the form a to the second minus 2ab plus b to the second. And so in this particular case, the term that takes the place of a is 5y. And the term that takes the place of b is 4, because b squared is the same as 4 squared. And then to check to see if this really is a perfect square trinomial, we can write down minus 2 times ab, so minus 2 times 5y times 4. And then if minus 2 times 5y times 4 is the same as minus 40y, then we'll know that it's a perfect square trinomial. And sure enough, minus 2 times 5y is minus 10y, minus 10y times 4 is minus 40y. So that is a perfect square trinomial. The two factors are identical. One factor is 5y minus 4. The other factor is the same, 5y minus 4. And you can verify by multiplying. There's a question on YouTube. Shouldn't we put the 1 to the left to the 4th power since it was already squared? No. This is 25 times y squared. The exponent 2 applies to y only. And since 25 is 5 squared, if we put in parentheses 5y and square 5y, that means 5y times 5y, which is 25y to the second. Yeah, so this is correct, the way it's written. So I'll just make a quick comment about the AC method. So AC method, if we multiply 25 times 16, we get 400. And two integers that have a product of 400 but add up to negative 40 are negative 20 and negative 20. Remember, if it's a perfect square trinomial, the two integers that you're looking for that satisfy the two conditions are always going to be the same. Negative 20 times negative 20 is 400, and negative 20 plus negative 20 is negative 40. So you could use the AC method and find the factors. Okay, let's move on to the next page. A difference of squares. A difference of squares has the following form: a to the second minus b to the second. So the word difference refers to the subtraction. So a difference of squares is just a shorthand way to describe that you are subtracting one thing squared from another thing squared. Okay, a difference of squares factors really nicely. The two binomial factors of a difference of squares are conjugate binomials. So the two factors of a to the second minus b to the second are a minus b times a plus b. They are referred to as conjugates because one has a minus sign and the other one has a plus sign, but they involve the same numbers, so a minus b times a plus b. And if you multiply a minus b times a plus b, we might as well do that. Multiply a minus b times a plus b. A times a is a to the second, and then plus a times b, and then minus b times a, but that's the same as minus a times b, and then minus b times b is minus b to the second. The two middle terms are like terms that add up to 0. Plus ab minus ab is 0, and so we just get a squared minus b squared. Okay, factor the following polynomials. (49m to the second minus 36). This is a difference of two squares. 49 is a perfect square because 7 to the second is 49. M to the second is obviously a perfect square. 36 is equal to 6 squared. So we can, if it helps, you can rewrite this as the term 7m in parentheses to the second, and then rewrite 36 as 6 to the second. And so since it's a difference of two squares, the two factors are conjugate binomials. One is 7m minus 6. The other one is 7m plus 6. And then you can verify by multiplying, if necessary, that you have the correct factors. Okay, 64y to the second minus 81. 64 is a perfect square. 8 to the second is 64. 81 is a perfect square. 9 to the second. So we can rewrite this, the term 8y in parentheses squared minus 9 squared makes it more obviously a difference of squares. So the two factors are conjugate binomials. 8y minus 9 is one factor. 8y plus 9 is the other factor. So that's all there is to it. The sum of squares has the following form: a to the second plus b to the second. The word sum, S-U-M, implies that we're adding, so we're adding two squares. So in this course, just remember, a sum of squares can be factored, but a sum of squares cannot be factored with coefficients that are all real numbers. So in this class, whenever you see a sum of two squares like this, 4x squared plus 9y squared, we'll just say that, for short, we're going to say that it cannot be factored, but it really can be factored. It's just that we're not going to learn how to factor it in this class. You have to go outside of the set of real numbers to factor a sum of squares. So non-factorable using real number or real valued coefficients. If you take college algebra, you'll learn how to factor a sum of squares in that class. It involves numbers that are not real numbers. Okay, we'll look at some examples of polynomials to factor. Factor the following polynomials: 64a to the second plus 112a plus 49. So the numbers look pretty big, since you're allowed to use those high-powered TI 30A calculators, though it shouldn't be too hard. So we might wonder if this is a perfect square trinomial because the term on the left is a perfect square and the term on the right is a perfect square. So maybe it's a perfect square trinomial, and we can test it. If this is a perfect square trinomial, it will have the form a to the second plus 2 times a times b plus b to the second. Okay, so the term that takes the place of a in this one is the term 8 times capital A squared. The term on the right, 49. So 7 takes the place of b because we have 7 squared. And we want to check to see if the middle term has the form plus 2 times a times b. So we'll write plus 2 and then 8 times capital A times 7. And sure enough, 2 times 8a is 16a, and 16a times 7 is 112a. So it is a perfect square trinomial. When you're doing problems in this section in Newton, most of the time you'll be given a perfect square trinomial to factor. But make sure that you verify that it's a perfect square trinomial, because maybe it won't be. And you'll get tricked into writing down two factors that are not correct. So we verified that it has the right form. So the factorization has the form a plus b times a plus b. So in this case, 8a plus 7 times 8a plus 7. If you were to use the AC method, if you follow the AC method closely and correctly, you can factor this using the AC method. So the first step would be to multiply 64 times 64 times 49. what I was thinking of, 64 times 49 is the same as 64 times the quantity 50 minus 1. 64 times 50 is just 3,200. And if you subtract 64 from 3,200, you get 3136. 3,136. And so looking for two numbers that have a product of 3,136 and add up to 112, or 56 and 56. Remember, if it's a perfect square trinomial, when using the AC method, the two numbers that you're looking for are always going to be the same. So you can verify 56 plus 56 is 112, and 56 times 56 is 3,136. So the numbers are large, but you could still use the AC method. That's the point. Okay, the next example, 75b to the second minus 180b plus 108. Well, 75 is not a perfect square. So by itself, this is not a perfect square trinomial. But remember the first step in factoring? Factor out the greatest common factor. In the previous example, the greatest common factor was 1, so we didn't have to factor anything out, since factoring 1 out doesn't change anything. So on this one, the greatest common factor is 3. So we want to factor 3 out of all of the terms first. So when we factor 3 out, we'll be left with 25b to the second minus 60b, and then plus 36. And now we're going to see if we can factor the trinomial that's inside the parentheses, 25b to the second minus 60b plus 36. So let's look at that over here in isolation, 25b to the second minus 60b plus 36. So we might wonder if this is a perfect square trinomial, because the term on the left is a perfect square and the term on the right is also a perfect square. If it is a perfect square trinomial, then it has this form, a to the second minus 2ab plus b to the second. If it is a perfect square trinomial, this will be the form, and the two factors will be a minus b times a minus b. Okay, the term on the left, 25b to the second, that's the same as squaring the term 5b. And the term on the right, 36, that's the same as squaring 6. And we want to see if the middle term, minus 60b, has the right form. We want to make sure it has this form, minus 2ab. Okay, so we can just write down what the middle term should be if this is a perfect square trinomial. So we write down minus 2 times 5b times 6. Yep, and sure enough, minus 2 times 5b times 6 is the same or equivalent to minus 60b. So this is a perfect square trinomial. So when we factor this one, the two factors are 5b minus 6 times 5b minus 6. Hey, but we have to remember, and this is especially important in Newton, if you don't want to get marked incorrect, the complete factorization of this original trinomial includes the factor 3. So we would write 3 times 5b minus 6 times 5b minus 6. Okay, and the next one, 16x w to the second plus 64x. Well, there is a common factor other than 1, so the greatest common factor. So what is the greatest common factor? When we compare the numerical factors 16 and 64.
Would it be 16?
Yeah, 16. 16 times 1 is 16, and 16 times 4 is 64. Each of the terms also has x. So we can factor 16x out of both terms. And then when we factor 16x out of both terms, we get w to the second plus 4. Okay, we did factor this much. The w to the second plus 4 is a sum of squares, so we cannot factor further. But if you see a problem like this in the Newton software, if you write down not factorable, that's incorrect, because we did factor it at least this much. So that's just something to watch out for. This is the factorization. We cannot factor further than this. Well, using real numbers anyway. So this is the complete factorization. Okay, moving on. 9c to the second plus 42c plus 49. The first term on the left is a perfect square, because if we square the term 3c, 3c times 3c is 9c squared. The term on the right is a perfect square. 7 to the second is 49. We want to know if the trinomial has this form, a to the second plus 2ab plus b to the second. So we can verify if it does or not. So in the middle, I'll write plus 2 times 3c times 7. And sure enough, 2 times 3c is 6c. 6c times 7 is 42c. So it is a perfect square trinomial. The two factors are identical, 3c plus 7 times 3c plus 7. Okay, we can do these next ones fairly quickly, probably. Just remember the first step in factoring. Check to see what the greatest common factor is. So the numerical factors are 16, 48, and said that wrong, 36, 48, and 16. So all of those are even, so we know that 2 is at least is a common factor. Is there a common factor greater than 2? Yes. 4 is a common factor of 36, 48, and 16. Since 4 times 9 is 36, and 3 is not a factor of 16, then 4 is the greatest common factor. So we can factor 4 out, and we'll get 9r to the second plus 12r times t plus 4 times t to the second. And now we want to check to see if the trinomial can be factored. So let's look at that over here by itself, 9r to the second plus 12rt plus 4t to the second. Okay, so maybe it's a perfect square trinomial. The first term on the left is a perfect square. If you square the term 3r, you get 9r to the second. The term on the right is a perfect square because if you square the term 2t, you get 4t to the second. So we test to see if the middle term is of the right form. So plus 2 times 3r times 2t. So 2 times 3r is 6r, 6r times 2t is 12rt. So it has the right form. So it is a perfect square trinomial. So the two factors are 3r plus 2t times 3r plus 2t. And then remember where we started. We started with this, which also includes the factor 4. So our complete factorization is 4 times the binomial 3r plus 2t squared. You can write it that way. Since I am about out of room, that will save me some space. Okay, the next one, 25c to the second plus 16e to the second. So those are perfect squares. 25c to the second is the term 5c to the second. And I'm adding that to the term 4e to the second. And then what? Well, using real numbers, we cannot factor this. So we just say not factorable. It really is factorable, just not with real numbers. So that's our answer. Okay, the next one, 81v to the second minus 180vy plus 100y to the second. The greatest common factor of all three terms is 1. So let's use the AC method on this one. AC method. So 81 times 100 is 8100. Two numbers that have a product of 8100 and a sum of negative 180 are negative 90 and negative 90. Negative 90 times negative 90 is positive 8100. And negative 90 plus negative 90 is negative 180. So if in the event we didn't recognize this as a perfect square from the start, by now we should know it's a perfect square. What's the reason? So remember, when using the AC method to factor a perfect square trinomial, the two integers that are needed will always be the same integers. So since negative 90 is the same as negative 90, that tells us that, oh, this is a perfect square trinomial. Anyway, we can proceed using the AC method. We replace the minus 180 Vy with minus 90 Vy minus 90 Vy, and then plus 100 y to the second. And then we factor the quadrinomial by grouping. So when we group the first and second terms, what's the greatest common factor? Well, 9 is a factor of 81 and 90, and v is a factor of v to the second and vy. So 9v is a common factor, and then when we factor 9v out of the first two terms, inside the parentheses, we have 9v minus 10y. And then you can verify by multiplying that we're on the right track. Okay, the middle operator is subtraction. So bring down the middle operator of subtraction. And that reminds you that out of when grouping the third and fourth terms, we're going to factor out the negative of the greatest common factor. So comparing the numerical factors, negative 90 and 100, the greatest common factor is 10. And then comparing the variable parts, vy with y to the second, y is the greatest common factor. So 10y is the greatest common factor, but we want to factor out negative 10y. So we write minus 10y. And then the binomial in the parentheses can be found by dividing. First divide negative 90 vw by negative 10y. So negative 90 divided by negative 10 is positive 9. Vy divided by y is v. And then positive 100y to the second divided by 10y is minus 10y. Okay, so the two factors are identical, 9v minus 10y, the other factor 9v minus 10y. Whenever the two binomial factors are the same, it means you just factored a perfect square trinomial. Okay, the next one. (121c to the second minus 36c plus 49). The term on the left is a perfect square. If you square the term 11c, you get 121c to the second. The term on the right is a perfect square. If you square 49, if you square 7, you get 49. So we're checking to see if this is a perfect square trinomial of this form, a to the second minus 2ab plus b to the second. The factors will be a minus b times a minus b. Okay, so if we construct a perfect square trinomial from this, what should I write down for the middle term?
2 times 11 times 7.
Yeah, 2 times 11C times 7. Hey, but what's minus 2 times 11C times 7? Well, let's see. 7 times 11C is 77C. And if I subtract that by -2, I get -154C. So is that a perfect square trinomial? No, it's not. This is not a perfect square trinomial. See, so it's a good thing we checked. Just because the first term and the third term are perfect squares doesn't automatically mean that it's a perfect square trinomial. This is not a perfect square trinomial. Okay, that doesn't mean that it can't be factored, though. It's possible to have a trinomial where the first and third terms are perfect squares, and it's still factorable. With integer coefficients. So we could use the AC method, 121 times 49. But I think with my remaining 3 or 4 minutes, I'm going to go back to the sheet that we were working on yesterday, where we did factor trinomials using the AC method. So we can get maybe 1 or 2 of these in. This is the last sheet from yesterday's notes. And we're going to use the AC method. So here we have r to the second plus 85rt plus 84t to the second. So the numerical coefficients that we want, the numerical coefficient of r squared is 1, and the numerical coefficient of 84t to the second is 84. So when we apply the AC method, we multiply 1 times 84 to get 84. And we want to see if we can find 2 integers that have a product of 84 and a sum of 85. Well, this pair of integers, 1 times 84, if we add 1 to 84, we get 85. So those are the integers, 1 and 84. We found those immediately. So that means we can factor this. So the next step in the AC method, replace the plus 85rt with plus 1rt, or just plus rt, and then plus 84rt, and then plus 84t to the second. And then we factor by grouping. Out of the first 2 terms, we can factor r out. And then we're left with r plus t. Bring down the middle operator of addition. Out of the third and fourth terms, we can factor 84 out, and we can also factor t. So we have 84t, and we're left with r plus t. Okay, the binomials r plus t match, so the complete factorization then is the binomial r plus t times r plus 84t. Okay, we're down to less than a minute. On the next one, though, we would, using the AC method, we would multiply 1 times negative 58, which is negative 58. And then two integers that have a product of negative 58 and a sum of 27. Well, if we use the systematic approach, we want to pick pairs of integers, one positive, one negative, but the one with the largest absolute value is positive. So our first pair, negative 1 times 58, and then negative 2 times 29. So negative 2 plus 29 is 27. So we found the two integers, negative 2 and 29. We're out of time. So remember, there's the home quiz that's due tonight at midnight. That's all we have time for today.